So I want to talk about the interpretations of the notion of a state in QM. So there are a few ways to do this, right? So in this course, we denote the state of a quantum system by omega. And obviously omega need not be a number or whatever, it's just a label, right? Now, we associate the state of a quantum system omega to a positive linear functional. Okay, so associated to each state, we get a rule which assigns a number to every observable, and it is linear, it is positive, so meaning that this must hold, and also that the expectation, or the value of the functional and the identity is equal to 1. Okay, so to each state omega, to each quantum state, right, quantum state can be equivalently represented by a positive linear functional, which gives which essentially gives the expectation value of any observable, or you can associate that in a bijection, of course, with a density matrix M, which is a Hermitian operator with the property that it is positive definite, okay, and that the trace is equal to 1. Okay, and the relationship between these two is that the expectation, so we call this particular linear functional the expectation. So the rule is that the expectation of A is equal to is given by this. Okay, so to each quantum system we associate a positive linear functional, and we associate a density matrix to that. Okay, now the physics is that for a quantum system in state omega, right, we have every observable for a quantum system in the state omega, every observable A in curly A defines a random variable. So that's the interpretation, right? So it defines a random variable which models outcome of measurement for corresponding physical parameter. So, for example, the Hamiltonian is an observable in curly A, where curly A is the set of Hermitian operators on Cn. Okay? Now I'm not saying anything about eigenvalues yet. I'm just saying that every observable defines a random variable, and that random variable models the outcome of a measurement, right? It's a random trial, an experiment, okay? Now, what is the connection with eigenvalues? So suppose that the state is omega, the quantum state is omega. Then we get a corresponding density matrix M, okay? Now, here's the important point. So A in curly A, which is the operator that represents the physical parameter that we're measuring. This is an observable, and suppose that it has eigenvalues lambda 1 up to lambda m. Okay, there are n of these, some of them can be repeated, so I'm just listing them in strictly increasing order. Okay, so there's a claim that there exists orthogonal projections Pj j is equal to 1 to m. Orthogonal projection is just a linear operator that obeys p squared is equal to p and that it is self-adjoint. Okay, so it satisfies this, okay, which is just basically the p squared is equal to p thing, but it's more specific. The sum from k is equal to 1 to m. So so p1, p2, p3 up to pm. So the sum of the pk's is equal to a. And importantly, you can decompose the entire operator into the eigenvalue times the weighted sum of the eigenvalues and the projectors. Okay? And we define little pk to be the trace of projection on M. Okay, on the density matrix. Now, here's the physics, right? So if you're in a state omega, right, and we have the observable A, and A has this spectrum right here, then we assign to this operator a discrete random variable little a, and the probability that little a takes. So essentially, we're saying that the outcome of the experiment can only be the eigenvalues of the operator, okay, and that the probability that little a happens to be the eigenvalue lambda k is given by little pk, trace of big pk times m. Now, there is a fourth and more familiar way to understand a state. So there are four ways to understand a state. Well, technically three actually. So we said that a quantum system is in a state omega, right? That's just a completely abstract statement. The second way to understand it is by means of a linear functional, which gives you the expectation of any observable that you throw in there. The third way to understand it is by the density matrix. And the fourth way, which I'm not really going to rigorously describe at the moment, is, of course, the notion of a wave function, right? So to each quantum state, you can associate a linear functional, or instead a density matrix, or instead a wave function, right? So to a state omega, we associate a wave function, which can be written as a superposition. So we're given an observable. We're in a state omega. We're given an observable little a. That's an Hermitian operator. Then what we do is we describe this state omega by a wave function psi, which is a superposition of the eigenfunctions of A, right? The eigenvectors of A. Okay, so where A lambda k is A psi k is equal to lambda k times psi k, and these are just complex. These are in Cn, essentially, right? Then what do? Well, we say, so this is the way we interpret probability. We say that the probability that the outcome little a is equal to lambda k is going to be given by the square of the modulus of ck, and of course that's provided that psi is normalized. You'd have to divide by the norm. Now, what's the connection between here and this whole business we did with the trace of density matrices? Well, let's look at the expectation of A, right? So the expectation of A is given by the trace of A times the density matrix, right? But on the other hand, from this formalism of quantum mechanics, we know that this is just given by, is this this is just given by this, and then divided by the norm, which is just 1. Okay? Well then, if you work this out, this just becomes the sum from k is equal to 1 to m of this, times by the eigenvalues lambda k. That's just the trace of am. right? And but we said before that the trace of AM, did we say that? Right, basically you can notice, yeah, so but we said, okay, but the trace of the expectation of A is given by this, right? So you can see here the connection between the PK we described before and CK. You can sort of guess. This isn't a rigorous proof, but you can see the connection between these two viewpoints.